Welcome everybody, can you hear me?
Sì, professore.
Okay. Can you give me a feedback about the video recordings of the laboratory activities? Have you seen them?
Professore, io avrei delle domande.
Mhm.
Posso chiedere adesso?
Sì.
Ok.
Wait, sorry, can we speak in English, please?
Yeah, I can try.
Traduco io se hai difficoltà.
Ok, vabbè, se può tradurre è meglio così.
Sì, c'è
Allora-
problema.
Ok, allora, nella prova di laboratorio 2 volevo chiedere, dal momento che poi viene richiesto di determinare il margine di sicurezza, volevo chiedere se abbiamo a disposizione il materiale del pannello,
Mhm.
in modo da poter ricavare appunto le tensioni principali e quindi con quello valutare il von Mises, eccetera. E poi un'altra cosa che volevo chiedere, che è più un dubbio che ho su quello che ha spiegato, quando facciamo il balancing del ponte di Wheatstone, noi stiamo già compensando le variazioni di resistenza dovute all'effetto termico, giusto? Cioè dobbiamo considerare la compensazione solo nel momento in cui durante la misura estensimetrica c'è un qualche sbalzo di temperatura, una qualche variazione di temperatura per la quale dobbiamo correggere tale misura, giusto?
Sempre per la seconda esercitazione?
Questa per la prima, penso, più che altro per la prima.
Ok.
Excuse me, Professor, can you start the recording before giving the answer because I want to have this answer?
Yeah. I'm going to translate these questions to everybody so that all of you is aware about some doubts from some of your colleagues. I'm going to record, however, the class right now. So your colleague is asking two questions actually. The first one is referring to laboratory 1 and the second the laboratory 2. Concerning the laboratory 1, he's asking about the temperature compensation. What you are doing when you are taking the measurements is just straight the measurement without any temperature compensation, okay? Because you are having a quarter bridge configuration, so the strain gauge is having all the temperature effects inside the measurement, okay? So what is your reading, regardless the method that you are using, is affected by temperature, okay? Temperature effects. In order to remove that, you have to take control, you have to have information about the operating temperatures, and then using the data sheet that I gave you or the compensation chart, you can estimate the compensating strain and therefore having the resulting temperature free, let me call that, strain measurement, okay, using the formula that we got together during the classes. The second question is about the laboratory number 2. In order to have the safety margin, okay, you need to know some details about materials, the material that we are going to use in order to have the reference yielding stress, for example. You don't have it, but you can refer to 2024 T2 aluminum alloy as reference. Okay. Is that okay? Or do you need at least additional discussion?
Potrebbe ripetere la Lega, ha detto?
2024 T2, 2024 T2.
Perfetto, grazie. Scusi, solo quindi un'ultima conferma. Quindi in pratica tutti i risultati che ha già messo nel datasheet per le misure delle misure estensimetriche sono da modificare con l'autocompensating chart direttamente da noi. E quindi dobbiamo avere e quindi dobbiamo utilizzare la misura della temperatura, della room temperature che abbiamo visto nel video.
Yes, indeed. So all the data that I provide you in the Excel file are strain
What did he
gauge
say? Can you
measurements.
translate what he said first before you
Yeah,
answer the question, please?
I'm doing that. I'm doing that. Um, the the numbers that you have in your Excel file are for all of these two laboratory activities are referring to the straight measurements. Okay, so you have to compensate that for the temperature using the compensating plot, the compensating curve that you got. So the question that you gave about the meaning of your reading is just there. It is just a straight measurement with no compensation. Okay. Any other question? Can you hear me?
Yes,
Hello?
Professor. Yes, we
Okay.
can hear you.
Okay. Any other question? No more questions? Okay. So let's go on with the classes. And now we ended the acquisition system part of the course. We dealt with the AD conversion and all the issues that are related to the AD conversion. So please review all these issues, review all the approaches that are used in order to reduce as much as possible those issues in order to have a very neat and clean and sound data set that you can use in order to do all your calculation, estimations, and so on. Okay. And by the way, this Friday we are going to have our laboratory activity number 3. It will be I try to do that using my computer on the line so that we can have some real-time results. Okay, I try to do that. If not, I'll give you all the files and we can just discuss about the the items that we have to consider in this next laboratory number 3. Okay. So now today we are going to talk about some structural dynamics modeling. Okay. I know that you all are aware about this structural dynamics modeling, but just to have a common language once again, I'm going to discuss a little bit the basic facts of the structural dynamics, most important things. So the first thing that I have to consider in this recall is what kind of system I'm talking about. The first very easy system that we have to consider is the single degree of freedom system. Why that? Actually, there is no reason why, because all the system, all actual system are no single degree of freedom system. It's a very specific, very peculiar system. But we are still talking about, we are presenting the single degree of freedom system just because the modeling of that could be extended also in a multi-degree of freedom system. Okay, so that's the reason why we are just stay on this single degree of freedom system because they could give us the path that we have to follow when describing multi-degree of freedom system. By the way, because we are dealing with experimental activities, we are dealing with a discrete system, that is a system that is described by a discrete number of degrees of freedom. Okay, so not a continuous one. Just the laboratory activity that we consider together, we have, for example, a cantilever beam that is a continuous structure in life. Okay, but we are viewing that from the eye of 4 points. So it is a discrete structure from the experimental point of view, because we measure the properties, the outputs that are strains, for example, in our laboratory number 1, but from the discrete I point of view. The same we are going to do with the structural dynamics. So we are talking about a multi-degree of freedom system as a general model, because we are referring to a system that is continuous in nature, but we are viewing at this system as it were made by a discrete number of degrees of freedom. Now, let's talk about the single degree freedom system. Okay, what is the general equation that is governing this the motion of the single degree of freedom system? It is the very easy one. By the way, my single degree of freedom system could be reviewed as a system characterized by, let's say, a stiffness, by a damper characterized by property C, and then we have the moving mass. And for example, my motion is fully described once I know the time evolution of my displacement x. Okay, if that is the system, just 1 degree of freedom, my equation of motion is the very well-known one, mx double dot plus cx dot plus kx, and that is equal to the forcing term ft. Okay, for example, we can have the forcing term there. And with respect to the previous analysis, that is, with respect to the analysis that we consider during our first part of the course, the forcing term, is a dynamic one, that is, it is time dependent. Okay, now if we are in the hypothesis that the initial conditions are homogeneous, okay, so assuming that x of 0 is equal to 0 and x dot of 0 is equal to 0, okay, that is the displacement, the value of our unknown function x, and the corresponding time derivative evaluated at the starting time, that is at 0 time, are all 0, then we can solve this equation in many ways. But if you use the Laplace domain transformation, then we can rewrite that equation as m p square plus pc plus k equal to x of p e, that is equal to the forcing term. In doing that, we are assumed that your x in time domain is given you by the amplitude and the Laplace dependency pt, okay, in which, remember, p is a complex quantity, and that is your Laplace variable. Okay, that equation is very, very nice, because we can call these quantities that are within the parentheses there as your z, that is dependent on p, and therefore we can rewrite everything as z of p times your xp equal to your forcing term. Okay, the quantity that is called z is also defined as your dynamic stiffness. Okay, and it relates just your input x with your input f with your output x, so that it recalls the behavior of the static stiffness when the Laplace variable p is 0. That is, we are in a static static behavior. This equation is very, very nice, but generally for our analysis, for our purposes, it is better to define, instead of the dynamic stiffness, we define the reverse of that dynamic stiffness so that we have a straight link between the input to the system and the output to the system, okay, from the system. And this equation is given you by x, that is dependent on the Laplace variable, that is equal to h of p times your f of p. Okay, please note that here we are having the input to the system and we are having the output to the system. Okay, therefore we can review your problem as the system overall is characterized by this HP. It is excited by a forcing term that is dynamic in nature, and then you are just considering what is the output of that. And this H function is called the transfer function. And maybe I can use different color. Yeah. Transfer function. And that is a very nice equation in which h, of course, of p is equal to the dynamic stiffness to the -1, so it is the inverse, okay? And we can prove, but it is very easy to do that, that it is equal to 1 over m divided by p squared plus c over mp plus k over m. Okay, so what we got here, we have two models of your structure, okay, of your dynamic system. What are these two models? The first model is this one, the first that we consider, and that is what I call the spatial model. Why that? Because we have all the parameters that are telling me what are the properties, the space properties of your system in terms of the mass, in terms of the damping, in terms of the stiffness of your system. This second equation that we got at the very end here, okay, this one is called the response model. The response model, because it's giving us the information how the system is responding once we know the input. Okay, so once we know the transfer function, then we can predict, we can see what are the effects of whatever input to your structure. And this relation, that is h of p equal to 1 over m and so far and so on, sorry, is telling you what is the relation between the response model and the dynamic model. Okay. And spatial model. We are always dealing with dynamic model, right? Spatial model. Okay. By considering that model, that is the transfer, the response model in terms of the transfer function, and because the relation, its relation with the space model, with the spatial model, then it is very easy to see that if your Laplace variable p is having some specific value, then the output of the system could be unlimited, could be very, very large compared to the input, okay, input level. And these values of your P could be found out just by solving what is called the characteristic equation, okay? Let me write that. So it is P squared plus C over M P plus K over M is equal to 0. And why that is important? Because it gives, okay, the poles of the system. Okay. Indeed, the solution of that the previous equation are generally called lambda 1, lambda 2. We got two poles because the degree of that characteristic equation is 2, so we have two roots, and this lambda 1, lambda 2 could be written as a the solution of that equation, that is negative c over 2m plus minus root square of c over 2m square negative k over m. Okay, now you know that there are some adjectives that we can use to characterize a system according to the different values of some systems parameters like c, m, and k. Okay, so the first one, if we have no damping at all, that is, if c is equal to 0, okay, then what we are having is system with no damping, and therefore the pole of that is just a complex conjugate pair, but here we are just imaginary part of these poles. Okay, so what we got is lambda 1 and lambda 2 are just equal to plus minus j k over m, square of k over m, in which j is, of course, the imaginary unit, and we define that k over m, your omega n, so plus minus j omega n, okay? This is, by definition, okay, the formation of the natural frequency of your system. Then system is having a damping that is a specific value that is called critical, that is so that the term under the root square is 0, then we have a critical coefficient, the damping coefficient. Okay, so let me write this. If C, so that we are having C over 2m square negative k over m equal to 0, that is, we are defining your CC, that is your critical damping, and this critical damping is 2m root square k over m. And what we are having is that the system response is not oscillating, is not doing that, is just going straight, that sense is not a straight line, of course, but is going to fade the response as the time goes by very smoothly, according to this value of this critical critical damping. This critical damping, in turn, is also used to define the damping coefficient. Okay, the damping coefficient is defined as the ratio, so zeta, and that is the ratio of C over your critical damping. Okay, please note that CC is just, that is the critical damping, is just the ratio, is just depending on the system parameter, that is the ratio that I considered before. If the system is characterized by whatever damping, then it is very useful, as we can see later on, to define this critical damping, that is the ratio between the actual C with respect to the critical one. Okay, or it is also sometimes used the amplification factor, okay, Q, that is the quality factor or amplification that is just equal to 1/2 over Z, 1/2 zeta. Okay, so this definition, the definition of the critical damping, is introducing me the information of the damping coefficient or the amplification factor, that is also recalled also as the quality factor. Okay, now the effect of having these coefficients could be seen when we are referring to the time domain solution of the homogeneous differential equation that we are considering so far. Okay, so the solution of the homogeneous differential equation, to be precise, constant coefficients, I'm missing that, homogeneous differential equation is x of t equal to x1 e to lambda 1 t plus x2 e to lambda 2 t, in which, of course, x1 and x2 are identified just by introducing the initial conditions. And of course, the poles of the system are very important because they are determining the nature of the motion that we are having. Because if your zeta is your damping coefficient is less than 1, it means that the system is having a under-damped response. If zeta, the damping coefficient, is equal to 1, that is, we are having the damping ratio that is equal to 1, and therefore the damping is equal to the critical damping, then we are having a system with a critical system response. If the zeta, the damping ratio, is greater than 1, then we have an over-damped response. Okay, and that could be easily seen from this time domain response of the homogeneous differential equation solution. Okay, so let me write that. If zeta is less than 1, then we have under-damped system response. Zeta equal to 1 critical damp system response, and having zeta greater than 1, we have over damp system response. Okay, by the way, we are also mainly considering this first one, that is system characterized by the damping ratio that is less than 1. Actually, the value of the damping ratio for when referring to typical aerospace structure that are made by light alloy materials or even composite materials are characterized by having the damping ratio that is no larger than 3, 4, 5%. If you are considering aluminum alloy, then the damping ratio associated to, let's say, cantilever beam is less than 0.1%. So I'm talking about 0.001%. So numbers are very small, but however, less than 1, positive, of course. Okay. The typical responses of such a system could be plot like the plot like this, in which we are having x of t, then we are having something like that, or let's say like this, or going down like this. Okay, so this is the typical underdown system. The critical one is in between the two, if you want, like this, and the overdown is that one. Okay, how can we say that? Mainly just by looking at the solution. If you are having your damping coefficient that is less than 1, the roots, the poles are complex and conjugate pairs, okay? And then we can rewrite those poles as a real and composed by real and imaginary part. So if we are having that, if theta is less than 1, then roots are complex and conjugate. That is, we can rewrite them as lambda 1 equal to, let's say, sigma 1 plus j omega 1, and lambda 2 equal to sigma 1 negative j omega 1. Okay, and of course the value of these lambda 1 and lambda 2 are referring to the system parameters. Please know that the sigma 1 is the damping, is called damping factor. Okay, the omega 1 is called damp natural frequency. Okay, and we can easily see that this damp natural frequency and damping factor are related to your system parameters as just the C damping is equal to it here. Okay, sigma 1 is equal to negative zeta omega n, and omega 1 is equal to omega n root square 1 negative zeta square. Okay, so that is very well known. I hope for you everything should be okay on your side when I'm writing those equations. Okay, just one remark, because the damping ratio about some then it follows that the time natural frequency is practically equal to the omega n. Okay. And then of course, once you are introducing your omega n, you can review the equation. Omega n is root square of k over m, and then zeta is the ratio between c and the critical c. Okay. Now, from the response model point of view, we can also introduce a different way of writing your transfer function. Indeed, we can use first the poles that we have found so far. That is, we can rewrite your H system transfer function. Remember, I defined that as the ratio between 1 over m divided by p square plus c over mp plus k over m. And because of our poles of the system, we can think to rewrite the denominator of that equation by using the poles that we just have. So we can rewrite that as 1 over m divided by p negative lambda 1 times p negative lambda 1 composite conjugate. We are just writing the same thing, but using this notation and using a serial partial fraction representation of that functional fraction, we can rewrite that as a1 over p negative lambda 1 plus a1, let me write that composite conjugate, p negative lambda 1 composite conjugate, in which these a's, a1 in our analysis, is by definition the residual term, residue, of your transfer function. And this residual term is equal to 1 over m divided by 2j omega 1. Okay? And that is another important parameter that is characterizing your response model. So we have to consider that your system dynamics has been represented by your space properties, that is the mass, damping, and stiffness, by the response model, that is by the system transfer function. Please note that the system transfer function here represented could be viewed as a complex function of the complex variable p. Let me add this information here at the very beginning. Yeah, okay. So here is HP is a complex function of the complex Laplace variable p. Okay, always remember that. And we can also rewrite that system transfer function as the summation of two components, one and its composite conjugate. And these components are characterized by the system property that is the pole and the system properties that is the residual term or residue itself. Okay. This transfer function that is just evaluated at the at the y-axis, that is at the real axis itself, or if you want at the imaginary axis, okay, sorry, it is also called the frequency response function. Okay, so we can write that the frequency response function is the transfer function evaluated at the imaginary axis. That is when P is equal to J omega. Okay, so we are having that your frequency response function, let me call that F frequency response function, or briefly H of omega, it is just your system transfer function that's dependent of the P when P is equal to J omega. Okay, and as we saw before, that is equal to the residual term divided by J omega negative lambda 1 plus its complex and conjugate part. J omega negative lambda 1 complex and conjugate. Okay. Now, this function, this frequency response function, as you can see, is just a complex function of a real variable that is simply omega. Okay. Yes, of course, omega is representing the imaginary part of the Laplace variable P. Okay, but omega itself is just one variable that is a real one that is spanning your negative infinity to infinity x-axis. Okay, so first let me consider, because the FRF is a complex function, let me write also that. Okay, the FRF is a complex function of a real variable omega. Okay, compared to the whole transfer function that is a complex function of the complex variable Laplace variable. Okay, before going on, because we are having that the frequency response function could be viewed as the summation of two contributions, each one having its complex and conjugate part on the other side. Let me consider a typical plot of this FRF. Okay, and let me consider, of course, the amplitude of that FRF. So let me see. Let me write. Sorry, draw this plot in this way. Okay, here on the y-axis, I'm writing my FRF in amplitude, or my H of omega in amplitude. In the x-axis, I'm putting all the omegas. Okay, there is a specific value that is the natural frequency, for example, here, and there. Okay, so we have omega n, negative omega n. So if I'm now plotting the FRS as the contribution of both A1 and A1 star, I have something that is like this. Let me pull up this in this way. Trying to do that. Okay. And then going down. And on the other side, I have practically the same, like that, and then, oops, right? Okay. Oh, okay, to the right. Okay, they are supposed to be the same. So the overall FRF could be viewed as the summation of these two curves, okay, as we had from the theoretical modeling. So the overall FRF, so this one, the first one is A1 constant conjugate divided by J omega negative lambda 1 constant conjugate. The other contribution here is A1 over J omega negative lambda 1. And so the overall FRF could be something like this. Not too much, sorry. So the green line is the actual FRF in amplitude. So what we can say from this is that the contribution of the constant conjugate part, okay, to the positive frequencies, for example, is immaterial. Okay, this part, okay, is not contributing at all. Okay, this part is not contributing. Okay, to the formation of FRF, okay, especially at omega equal omega n. Okay, moreover, the complex and conjugate part is symmetrical with respect to the y-axis. Okay, so what we can say is that we are completely forgiven. Okay, we are completely not considering at all the negative frequency part of our plotting. Okay, not consider. Okay, because the contribution to the real part is negligible and the missing part could be synthesized by the information of the positive frequency part, just because the behavior could be symmetrical if I'm considering the amplitude, or if you consider real part is an imaginary part is antisymmetrical. But we can reconstruct it, we can resynthesize this missing part, so we can just focus on the positive frequency side of your FRF. And that's the reason why you are always referring to the right-hand side of this plot, of the FRF plot, because the negative, that is the one characterized by positive frequencies, because the negative frequency part is the same as is not contributing at all to our behavior. This is once again a two-side function, two-side because we have both positive and negative frequency, but we are considering one side FRF because it is the positive one, because we are considering what we already discussed about. Okay. The time domain representation, so the evolution of this FRF, or this frequency response function, as you already know, is called impulse response function. Okay. That could be obtained by taking the inverse Laplace transform. So by taking the inverse Laplace transform, okay, of the transfer function, we are having your impulse response function that is equal by A1 e to lambda 1 t plus A1 composite conjugate e to lambda 1 composite conjugate t. Okay, or if you introduce the real and imaginary part of your system pole, what you got is e to sigma 1 t times e1 e to j omega 1 t plus e1 composite conjugate e to negative j omega 1 t. Okay, so we got the same behavior that we already see, as we already saw in the frequency domain. Okay, so the residual part, if you want, the residue is giving the amplitude of the oscillation okay. The real part here of the pole is giving the attenuation, okay, or if you want the decay rate of your system response, okay, and finally omega 1 there, okay, the imaginary part of the pole, okay, gives the frequency of the oscillation. Okay, so these are the different contribution. So once again, if you would like to plot your impulse response function in the time domain, okay, you got this your ht, so you got initial condition, let's say like that, and then going down, for example, like this. You remember we have a decay that is given you by sigma, your period t is equal to 1 omega n, remember, and the amplitude here is related to the residual term. Okay, now let's have a break, let's say about 5 minutes, so let's resume at 3:15. 15, even something earlier. Okay. Questions?
Excuse me, Professor.
Mhm.
Can you
Yes,
show me the last equation, please? The last one.
this one.
Yeah, this one. Yeah. Thank you.
Welcome.
Professore, scusi, posso chiedere un chiarimento sulle modalità d'esame?
Sì, prego.
Per quanto riguarda soprattutto la parte della stesura dei report, è
Mhm.
un qualcosa di obbligatorio nel senso che se non lo facciamo non è possibile fare l'esame, oppure è un qualcosa che serve a noi e quindi magari
No, no.
possiamo effettuare lavoro su questo?
Serve a voi, semplicemente serve a voi. The student is asking about the final exam and the role of the reports concerning the laboratory activities. As I already said many times, these reports are not mandatory, so it's up to you, student, to decide whether or not to write them. Okay, you have time to submit those reports, let's say about 1 week before the exam date, so that I have the time a little bit to review those reports. Okay, and then if you submitted those reports, your first question of your final exam will deal with those reports. That is, I'm going to pick one of these reports and I'm asking you to describe what you got, describe the methodologies, describe the result that you got, describe some very critical parts. So it is intended to you first to get acquainted with some, let's say, virtual laboratory activities to the subject itself, and the aim is to, let's say, start your final exam a little bit more relaxed. Okay. So far, I'm not sure about how this final exam will be carried out. Let's say that is, I'm not sure if I can take you an oral exam face to face, or it will not be possible, and therefore we have to take that using synchronous and using Google Meet or something devices that can allow you to have the exam at the same time but remotely done. And in this case, I'm not sure if I can if I can have the oral exam, or if I have to ask you to write my oral exam to write on a paper, and therefore I will let's say see what you wrote about the questions. Okay, and that depends, of course, on the virus. If the virus is still up and, and running, then we have to do this last option.
Professor, so when you say it is not a mandatory,
I can't hear you very well. There is a lot of feedback. Can you repeat the question?
sorry, is it okay now?
Yep.
Okay, so when you say that these reports are not mandatory, does it mean that we can participate in the exam without giving this report? Or
Yes, sure, sure.
so if we participate in the exam without this report, how is the first question that you said?
Some other questions concerning more theoretical parts, of course.
Okay, it means that we should solve a problem. Am I right?
Yeah, something like that.
Okay, thank you. And the exam is in a way that you gave us a mock test.
Yeah, I think so, something like that. But it depends on the virus. So to be on the safe side, let us consider that your final exam will be asynchronous remote exam that maybe is using the exam.net. So all my question that I would have given you orally in with an in-person exam are giving you on a text, okay, and therefore you have to answer those, let's say, quoted oral questions in a written way, okay. For those
Okay,
of you that are submitting the reports, the first question will be something related to the report, okay. On the contrary, who is not submitting any report, that's the same. The first question will be on a theoretical part or a little bit of some analysis of some results. Okay. Okay. Is that okay? Any other questions concerning the exam? Okay, so let's keep going on this impulse response function or on this analysis of these system properties in terms of the frequency response function. And now let me see what is the effect of changing some system parameters in terms of the mass, stiffness, or damping to the overall behavior, that is to the frequency response function itself. Okay, so let me consider, for example, one reference FRF, that is frequency response. Your FRF, positive frequencies, we already discussed about the meaning of considering just the positive frequencies. Here we have the FRF, H in amplitude, okay, and then let me have your reference FRF like this. Okay, as you remember, we are having the peak of the response is happening at the frequency equal to the natural frequency. Now the question is, what happens when we are having the need to change your pole, your natural frequency, because maybe there is the natural frequency of the system and the excitation frequency are too close to one each other. So if we are changing the stiffness, the effect is something like this. So if we are considering this, Okay, those plots are obtained by having the same system properties, but changing the stiffness. Sorry, I use low. Okay. And I am increasing the stiffness. So as you can see, by increasing the stiffness, the value of the omega 0, okay, of your H, that is the stiffness, this, yes, the flexibility is reducing, okay, and that's because we are increasing the K, the stiffness, of course. We are moving away from the reference value, so we are moving to the right, your actual value of the natural frequency, okay, and this part, the higher frequency contribution, is practically having no effect of the change of stiffness. No effect, because of changes of K. Changes of K. Okay. On the contrary, here we have the area with evident or higher with higher sensitivity to changes of the stiffness. Okay. And as you can see, we can assume that there is a sort of horizontal line that is, let's say, representing the asymptotical behavior, okay? And these are called the compliance line. Okay. So if you would like to change the stiffness, you can do that. The first effect is to move the peak of resonance at higher or lower values according to the different value of K. The higher frequency behavior is practically insensible. There is no sensitivity effect at higher frequency. On the contrary, the maximum effect of this change of stiffness could be viewed at lower frequency, and this effect could be represented by what we call compliance lines that are, let's say, sort of interpolating lines, horizontal line to the FRF at very, very low values of the frequency. Now, let's see what happens if we are changing the mass. Let me redraw the same plot as before. So, yeah, having same plot. Same function, the FRF, in terms of amplitude. The reference is always there. Okay, now, if we are considering a change of the mass, an increase of mass, we are having curves like this. Okay, so we are moving here with an increase of the mass value. Okay, and here at very high frequencies, we can have the maximum effect. Okay, so here we got the area with higher sensitivity to changes of the mass represented by the so-called mass lines. Okay, that are some straight lines, like the ones that I consider. Finally, if you consider the effect of the damping, we can have a drawing like this. Let me consider the reference one once again. Okay, now if we are changing the damping, what we can have is something like that. Okay. So the most important line in this, we'll consider the change of the damping. Okay, here we have C equal to 0, and then decreasing C. Okay. So what we got here is the effect of the change of C is higher, okay, close to omega n. That indeed, because we are considering the damn natural frequency, then we have also to consider a little change of the value of the natural frequency itself. Okay. That's it for the single degree of freedom system. Now let's consider a multi-degree of freedom system. Okay, so multi-degree of freedom system. And let's see how we can represent that. We already discussed that this multi-degree of freedom system could be viewed as the actual measurements, okay, that are defined over a certain number of measuring points. But however, here in this representation, we are considering that your unknown quantities x are all recorded in a vector. Okay, this vector is real vector having n components, and once again they are the Lagrangian variable vector. Okay, or n components. Because of that, the stiffness, the damping, and the mass matrices are all real matrices, dimension n by n, and the forcing term is a vector of forcing terms, real, and of course having n components representing this external force level. What is the equation of motion? The space equation of motion, or the spatial model, okay, is mx double dot plus c x dot plus k x equal to fg. Okay, and that is what I call the spatial model. Okay, now if, as we already consider, x0 is 0 and then x dot 0 is 0, that is, we are considering the system evolution starting from homogeneous initial conditions, then we can consider the Laplace transform, okay, as we did before. Laplace we got that your p square m plus pc plus k times your x p is equal to f of p. Both the x and the p are complex quantities, generally speaking, and therefore we can define this quantity, this function of the Laplace variable p, as the dynamic stiffness matrix, so the C, as we already defined before, so that we can have the equation of motion, the Laplace domain, that could be written as Cp times your x p equal to your f p. Okay, and this C is the dynamic stiffness matrix. But because we are very interested in having the link between the input and the corresponding output, we can define the system transfer function matrix HP, system transfer function matrix, okay, that is equal to your inverse of the dynamic stiffness matrix, okay, and so that we can have that your actual output is linked to the input through this system transfer function matrix, okay, that is your input to the system and that is your output, okay. Now if we would like to have the power is single degree of freedom system, then we have to consider that if we are interested in the homogeneous part of this overall governing equation, we have to set to 0 this forcing term F, but however, the modal equation that we are leading is not the one that we have in a canonical form, okay? So the previous equation is rewritten by just making some manipulation, so making a little bit of fun of algebra. So when referring to this equation, let me call that as triangular equation. So in order to have the triangle equation in the standard eigenvalue problem form, we add just an equation, and this equation is this one, Pmx negative Pmx equal to E0, okay? And of course, this 0, it has been added to the previous equation. In the Laplace domain, like this, then we got x, sorry for it, and that is equal to f, that is forcing term. Okay. Now, by setting this new unknown variable y, it is a function of p, as a collection of the px component and the x component in the Laplace domain, we can rewrite the same problem that is expressed by the triangle equation as let me write that here, 0 m c, these are submatrices, times p plus negative m 0 0 and k, okay, and everything here is multiplied by the new unknown vector px, and then x, that is equal to 0, and then the forcing term. Okay. Now, by calling this matrix as matrix A, and by calling that as matrix B, the problem could be written as PA plus B times Y is equal to F prime. And of course, that is the F prime forcing term. And this is the standard. This leads to the standard eigenvalue problem when looking for the solution of F prime of b equal to 0. Okay, so we made this, let's say, algebra, a little bit of algebra in order to do that. So the standard eigenvalue problem could be obtained, so the eigenvalues of the system could be obtained just by looking to the characteristical equation that is obtained by solving this equation. Oh, sorry, B, not A. Equal to 0, that is the characteristic equation. Please know that from here we having 2n eigen values, and these are 2n complex and conjugates. Okay, and the result could be recast in a sort of matrix, diagonal matrix of capital lambda, like this. So this is a diagonal matrix lambda that is made by all the eigenvalues, that is the poles of the system, lambda 1, lambda 2, up to lambda n, and then lambda 1 comps and conjugate up to lambda n comps and conjugate. Okay, remember the lambdas are having both a real and imaginary part, so sigma 1 plus j omega 1, sigma 2 plus j omega 2, up to sigma n plus j omega n, sorry, up to sigma n complex conjugate plus j omega n complex conjugate. Okay, in which your rth component of the r lambda, so r lambda pole, okay, is omega r, and that is the rth damping factor, as we already defined. This is the rth damped natural frequency. Okay, that is equal to negative zeta r omega n r, and that is equal to omega n r to square 1 negative zeta r square. Okay, so as you can see, we got the same results as we already had when dealing with a single degree of freedom system. But now what we are having is just all the modes together are acting in order to have the final motion of the system. When we were referring to a single degree of freedom, there were not just combination at all. Now we have all the combinations, all the modes that are all considered together. As we define the lambdas, the matrix of the poles lambda, we can also define the matrix of the eigenvalues, eigenvectors, sorry, and this could be defined as the phi matrix, that is the matrix of the eigenvector, that could be defined as lambda 1 psi 1 vector, and then the psi 1 vector, okay, as we define the new unknown vector y, then lambda 2 psi 2 vector up to the lambda n psi n vector, and then all the constant conjugate, lambda 1 constant conjugate psi 1 complement conjugate up to the last one. Lambda n complement conjugate psi n complement conjugate. And of course, the other one are simply psi 2 psi n psi 1 up to the last one, psi n complement conjugate. Okay, and please remember that all the psi are vectors, complex quantity, okay, dimension n. The overall dimension of this is 2n times 2n. Okay, and that is the effect of having played with the with algebra in order to have the eigenvalue problem reduced to the standard eigenvalue problem of your system. Having said that, we can also demonstrate that your system transfer function matrix HP could be also reviewed as a linear combination of your model, your CS model parameter from 1 up to n, okay, it is AR divided by P negative lambda R plus AR constant conjugate divided by P negative lambda R constant conjugate, okay, in which here we are still defining the quantities AR that are the residual terms that this time they are matrices. Okay, we can prove that these residual terms, okay, could be written as this quantity QR times psi R transpose, okay, and the QR are what they are called the amplification factor, okay, modal amplification factor, okay. So what we got so far is the same representation as we got for the single degree of freedom modeling, but this time having more than 1 degrees of freedom that has to be considered. Now, I would like you to introduce the overall general relation between the model and the response model by introducing the modal vector matrix. So the modal vector matrix is defined as B, okay, as all the eigenvectors that are represented in each column. So psi 1, psi 2, up to the last one, psi n, and then psi 1 constant conjugate, psi 2 constant conjugate, up to the very last one, psi n constant conjugate. Okay. We can also define the diagonal matrix of the eigenvalues. So we can define your pi negative big lambda to the -1 as the diagonal matrix whose elements are 1 over p negative lambda 1, 1 over p negative lambda 2, up to the last one, p negative lambda n, and then 1 over p negative lambda 1 constant conjugate, And the very last term, 1 over p negative lambda n constant. Okay, so it is a diagonal term and diagonal matrix like that. Then we got the modal participation. Oh, sorry. Participation factor matrix L that is defined as L equal to the modal amplitudes Q1 psi 1, Q2 psi 2, Qn psi n, and then to the last term Qn constant conjugate psi n constant conjugate. Okay, or if you want, that could be also defined as the diagonal matrix Q, which we have all the participation factors Q that are recast in a diagonal matrix times the modal vector matrix. Okay. So as a matter of fact, this L is referring to how the input will be projected to your system in order to have the output. As we can see that your H could be rewritten in terms of modal vector matrix times your diagonal matrix of the poles, Pi negative b lambda to the minus 1 times L. Okay, or that is the same H P is equal to B times the eigenvector, sorry, eigenvalues of the eigenvector, and then the diagonal terms of the participation factors, and transpose that the same. This is the most compact form of the frequency response function and relates the modal domain, the modal representation of your system properties with the response model. Okay, if we now consider the response, therefore we have just to consider the input. Okay, so my X P is equal to your H times your F P F of P, and that is equal to V P I negative large lambda to the minus 1 L, and then Fp. So that is giving you straight in the frequency, in the Laplace domain, your system response. When you are referring to the frequency response function, okay, F for F, then what we got, as we already have in the single, we're referring to the single degree of freedom system, but now we are having a matrix. Once again, that is TB vector matrix times j omega I negative your poles to the minus 1 L. And if you consider all the residual, what we got, okay, that is equal to the summation R from 1 to the number of moles that are there, your QR psi R psi transpose divided by j omega negative your lambda R plus the complex and conjugate part QR complex and conjugate times psi R complex and conjugate psi R emission divided by j omega negative lambda R complex and conjugate. Okay, and as we already considered and discussed when referring to the singular degree of freedom, we can review the overall frequency response function in the whole frequency range, positive because we are not considering the negative side of the frequency range, as the contribution of each individual mode, each one that is weighted by the participation factor QR and having its own natural frequency at the omega R. Okay, so we can review this by referring to this plot in which we are having as function of omega the amplitude of your FRF. I'm just referring to the h of omega. Okay, and then we are having that the overall FRF like this, it is having many poles with respect to the previous one. Okay, so this is, for example, omega n1, this is omega n2, omega n3, and so on. The other could be reviewed as a linear combination of all these components. Okay, so what we can have is something like this, and then going down, something like that, and then going down, something like this, and then going down. Okay, each one is whatever term that is included in the summation sign. Okay, and this is the rule. Okay, so the frequency response function as a function of the all the modal contribution. Okay, so the f okay could be rewritten in terms not the FRF, the response in the FRF domain, the frequency domain, the response in the frequency domain is just x of j omega, to be sure if we are referring to that. Okay, v, the modal participation, the modal vector matrix, sorry, then j omega I negative lambda to the minus 1, and then the forcing term. In the time domain, we are having is your impulse response function matrix. This that could be reviewed as once again the product of the modal vector matrix times your diagonal matrix of the exponential matrix A to lambda t, okay, times the modal participation factor, or if you want, the combination, the linear combination from 1 to the number of modes of your QR psi r transpose e to lambda r t, okay, plus QR constant conjugate of psi r constant conjugate psi r emission times e to lambda okay, to lambda r constant conjugate time. Okay. Okay, I know that I went very fast in describing these modal, these dynamic properties of whatever system passing through the space domain, so the space model, the response model, the modal model, okay? But I think that all of these subject has been already considered during previous courses. So that's the reason why I just had a very quick look to that, just to have your final representation of final equations that are referring to what is the relation between the modal parameters and the response model and the space model. Just to be linked with the experimental activities, let me consider that generally what is happening is that the number of modes is less than the number of output, number of degrees of freedom of the response. Okay, we can have 3, 4, 5 accelerometers, for example, and we can have, let's say, 10, 20 modes that we can see. Okay. Moreover, the number of outputs is generally less than the number, okay, of the whatever number of modes, okay, that we are considering in our modeling, and the number of inputs, number of degrees of freedom, okay, of the input, okay, is much less than those available for the output. Okay, generally they are up to 1 to 5, no more than that. Okay, so what you are having in reality is that your whatever response in the frequency domain that could be viewed as the frequency response function times your whatever input, okay, is a vector of n1. The h is generally no times ni, and of course that is ni times 1. Okay, if you look at with the relation with the modal parameters, remember, just rewrite that here, j omega is equal to v times j omega I negative capital lambda 1 to L and f j omega. So what we are having is that this vector is, of course, dimension NO times 1, number output. The modal vector matrix is defined over a number of output that is equal to NO, and then we can have 2m, and m, sorry, not m, sorry, 2 and m. Okay, that matrix is, of course, 2nm times 2nm. The modal participation factor is the projector of the input to the output, so passing through the modes, so nm times ni, and finally the forcing term is of course ni times 1. Okay, so that is the final recall when referring to the dynamical system like this one. And if there are no questions, the class is over right now. If you have any question, I'm here.
Professore, in una riga ha scritto, ha usato una H, dove potrebbe rispiegare che cos'è? Sarebbe complesso completo trasposto?
Hermitiano, Hermitian.
Ah, ok. Va bene.
Let me, yes, this one. Hermitian. Complex and conjugate plus transpose. Any other question? Ok.
Professore,
So, see you
se
tomorrow.
posso,
Ok.
se posso, solo un'ultima domanda sul laboratorio.
Sì.
Ha detto appunto che nella seconda attività il materiale è alluminio, però a quel punto nell'estensimetro non abbiamo l'autocompensating chart che è relativo all'acciaio?
Yes. So the question is that because in the laboratory number 2, the material is an aluminum alloy 2020-42, the question is, because the data sheet is referring to the compensating chart with respect to the steel, you have to take some action about that. The answer is you have to take some actions. Okay?
Va bene, grazie. Quindi correggiamo, insomma, dobbiamo cercare di correggere.
Yes, if there are some specific errors induced to the fact that you are using an actual material that is different with respect to the calibrating material, then you know how to evaluate this error because you are using a strain gauge on a different material than the one that is designed for.
Certo, va bene. Grazie mille, professore.
Okay. Other questions?